Okay, I think we're away. Hello, this is just a quick chat about EEE 502 being used with the Millennium boards and how you actually can get your first program working. So what you see in the video in front of you is a Millennium board. Obviously a large number of parts. Look at it fairly carefully. That's your processor. There's writing, very faint writing on it. It should say something like PIC 16F877. There's a little metal can here which is the oscillator. Make sure it's plugged in correctly. It does slip out. That's your on-off switch. There's a 5-pin socket in here which is used for the programmer, and then you get access to all the I/O ports by this line here. Obviously you see there's lots of ones wired up here, and we'll build on those as the weeks go by, but today let's just get an LED going. Make sure that you're plugged in with a 12-volt supply with the center pin positive. There's two wee arrows on the plug. You can just about see them. Two little arrows on the black plastic that need to line up whenever you have a symbol there that has got a center pin positive. So it's quite hard to see, I'm afraid. If you look at it in real life, it's a bit easier to see, but 9 volts will work, but 12 volts is better. Okay, when we switch it on, there's a slight faintness probably visible on the LCD. Most of them seem to do this. You can adjust the contrast with this. We'll probably not use the LCD in this class, so it's not too important, but it lets you know that the power's on. Okay, now we have the PIC kit programmer. This is a PIC kit 3, it's red coloured. We also have PIC kit 2s, which are black coloured. There's a 6-way connector on the end, 6 holes there, and pin 1 is marked with a white triangle. Now we need a special adapter lead. This adapter lead has got 6 pins in one end and 5 pins in the other. The 6-pin connector is plugged into the PIC kit, with the unused pin as pin 6. So if I plug that in, you'll see there's an unused pin here, and pin 1 is wired up like that. The other end, with its 5 pins, one of the wires is coloured red, and that goes near the outside of the board. So if I can just plug that in like that, hopefully down at the bottom there, left in this case of the board is the red wire for the 5-pin. Okay, that's us, I think, finished with the video. I'll move it away. Now we have the MP Lab X IDE, and let me close this project and save everything. And what happens then is that we have an opening screen. One of the options for it is to create a new project. This is a new project wizard. Always worth using it because there's lots of intermediate files and folders created, and you don't want this done in the wrong place. Be aware that MP Lab X is fairly strict about the length of path and the name of any of the subfolders in the path, as well as any file names you create. So don't use a path name with spaces in it. Keep your path names short. Make sure your file names or any folder name does not begin with a digit or an underscore. So be fairly defensive to make sure that this works. Okay, I'm going to click on the Create New Project. What we want is a microchip embedded standalone project, and click Next. What we need to do then is pick our chip. If I switch to the mid-range first, it'll restrict the number of choices here, and I know it's down about halfway, 2/3 of the way. I'm going to select the PIC 16F877 because that's what's on my board. There may be boards with 877As on them. The only difference between those two is the algorithm that the programmer uses to physically program the chip. You as a C programmer will not notice the difference, but the programmer would. So make sure that that matches your chip. I'll show you later how to change it. Select your programmer. In this case I'm using a PickKit 3. It should see the serial number there for PickKit 3. I don't think it does for the PickKit 2 if you have a black one. Pick your compiler, which in our case is XC8. Now, this is the place where you don't want spaces or strange characters in your path or your folder name. And every project should get its own folder. So I'm actually going to go up a level. What I did is I created a folder on the desktop using this icon, and I'm going to go in there and create. I'm going to go in there. Nope, I'm going to go up a level. No, I was right the first time. Go in there and then create a new folder called Program 2, because I was testing this earlier. I'm going to make the project name Program 2 as well. Now note that this says set as the main project. That's important because you can be looking at one file, and when you push the compile button in the IDE, it only compiles the main project, and that can be a source of a lot of confusion. That's us finished, and it should create all the folders and things that are needed. And up here on the left is the project navigator. You'll notice that P2 is in bold. If I wanted to change any of its properties, I would right click. I'll do that now. Right clicking in P2, it lets me set as the main project. I don't need to do that because it's in bold. And if you, under properties down here at the bottom, you could change any of the things we've set up before. That's probably the only things you'll need in there. What we will need to do is go to source files and right click new main file. You can call it whatever you want. It's probably sensible to call it the same name as your project. You could even call it main.c if you wanted. And a template comes up. Now we need to change that a wee bit to suit what we're trying to do. If it's an embedded system, we have to hash include xc.h. Once we do that, we have access to any of the SFRs, special function registers, that let us access the peripherals of our chip. I should say that at the top of every program we should have the file name, the author, maybe a version number, and we can lay that out whatever way we want, but we should document in two different places at the top, or at least two different things at the top. You can leave it the way it was before, but you need to get in the habit of documenting. Later on, we may choose to define version like that and then print a message so we can tell what version we're actually running. So commenting should be at the top. There should be file, author, version number. There should also be a description. So we're just going to blink an LED. So two things at the top. Each individual variable that you declare should be documented. And what we're going to do actually, we're going to go into a loop. I'll nip down there and put a while 1, which is always true. So that will loop forever. That one will never be reached. That's the end of our main. Always worth commenting it. And then in the body of our loop, what do we have to do? Well, sorry, before we get in there, things in uppercase that are from the data sheet are known by the compiler because they've been defined in xc.h. So the tri-state register, the trice register for port E is where we define inputs and outputs. If you think of a 0 as being a bit like an O for an output and a 1 being a bit like an I for an input, if we put a pattern of 0 in there, either in hex or in binary, that lets port E to be all output. if you look at the data sheet, you'll see port E is only a 3-bit port. So port E can go, if we put bit 0 out as a 1. In fact, let's do this differently. Port B, I'll just stick the hex there. Stick 0s out in port B, and then stick 1s out on port E. Then all we need to do, that will certainly go on, off, on, off, on, off in a big loop, but we need to have a delay. So for the minute, we'll just say I equals not, I less than 20,000, I plus plus, and we'll not do anything, so that's just like a null statement there, and that means it'll create a slight time delay, hopefully, unless the compiler was clever enough to optimize it out. But that's our program ready to go. Since we declared int with a main with an int return value, we have to have a return statement. We could actually put a void there and delete that statement. Doesn't really matter, it's never reached anyway. I'm going to make this window a wee bit bigger for us. Okay, you should really clear those. Remember how? Clear, Control L. So when you get yours, that's just what it's going to look like. Okay, to build the program, this arrow here, be careful that you don't build it with any debugging options. It's the first one, make and program the device main project. If you just wanted to compile it, under the run menu, build the main project. Okay, so I'll make and program. My program is plugged in, there's power on the board, and I might be able to bring back the video and we'll see some lights change there maybe, but make and program. So in this bottom window here, the output window, it's telling us that make is running. It's compiling the program. Any errors that pop up will be listed there. If you double click on them, they'll take you to the line number, which might be the one after the line number that the errors are. We don't need to, I've checked that we are on a 5-volt system, so that's okay. It found a target, a device ID of 6. If the wrong chip, if an 877A was in there, you'd get a different message, and I would say you'd have to go to the project properties up here, right click and change the project properties for the new chip. So it says the program's complete. Okay, next thing to do then, what I should have done beforehand probably, is actually wire up our device. So we've got a little bit of wire here. You should have pointy nose pliers and snips. There's a fair bit of skill involved in this, but you should be able to strip off about 8 millimeters of wire, and hopefully you can see the metal part there. And then with the pointy nose pliers you can plug this into RE0, push down. I can then bend this nice and neat, cut off our spare, and again I've got some bare wire there now, and then I can bend that down and plug it in and tidy up the wiring a wee bit, and that's an LED blinking. You've written your first embedded C program, and after this the rest is just detail. Well done.